Good afternoon. So I'm Piotr Weglicki, I'm a marketing manager at AMD. Now this session will be about secure encrypted virtualization. So we'll live in a time of unprecedented security threats, and we can see it going across the board. Attacks on commercial organizations, on government, on educational institutions, everywhere. And we see that the average, there has been some study done, and it estimated that average, when you go across all of these threats, the average cost of that is $7 million. But we all can recall much more impactful and more costly threats that has happened going into hundreds of millions of dollars. There was another study also done by IBM, which concluded that 40% of the threats is coming from the inside. And this is a frightening number because, how do you protect against the insider? So at AMD, we treat investment into security technologies extremely seriously, and we put a lot of resources into that. And what we develop a range of different technologies that help to secure the systems, and securing servers and other systems from a boot up to the shutdown of the system. And there are three types of protections that we do. So first of all, there is a secure root of trust technology, which enables us to make sure that if our customers are booting their system, it's from a trusted source, from a code that that is yours, and that a hacker has not actually modified that and is not going to hijack your equipment. The second type is secure run technology. So this is maintaining the integrity and security of the systems while running. So protecting against all of the threats while the system is in operation. And the final one is during the shutdown and also during the move. When you're moving actually VM from one server to another, we've got technologies that secure that. And there is one area that I think is overseen by the industry quite significantly, and this is memory, protecting the memory. So when you think about that, if we are storing any data on a hard disk, it's automatically encrypted. If you've got a transmission of data, it is end-to-end encrypted with IPsec. But what happens once you reach actually the end node? Okay, this data is terminated into a memory. And this memory is a plain text. It's completely open, and if someone knows how to exploit this, can get all of the data, very sensitive data, whether it's, including if you are a private user, can get your credit card number. If you are a corporate user, it could get, all of the key data about your corporation that you are trying to secure, or even as bad as the encryption keys. And with this in mind, at AMD, what we developed a range of technologies. And what I will focus on today, it will be these two technologies, which is secure memory encryption and also secure encrypted virtualization. So what type of attacks we are protecting against? So let me start with the physical access attacks. So these are when the perpetrator actually has a physical access to your system that can actually either install an equipment that will be able to read your memory, or can actually freeze spray your DIMMs and take out them and read it later. Or with a new technology, non-volatile DIMMs, just remove the DIMM and read it. And against that, the technology that we've developed is secure memory encryption. There is another attack that it's more coming from the access attack, user access attacks, and that will be in a case of administrators who are able to scrape the memory. It's extremely simple. We've demonstrated actually, it's a simple line of code that can actually get access to your memory and see exactly all of the data that has been stored on the memory. It could be the situation that administrator injects a certain code into your machine and into your VM, and will be able to exploit that. But also, these are sort of vicious attacks coming from an administrator. But it could be even things like a hypervisor, which any technology is not 100% perfect. Can have bugs, can be leaky, and can leak the data, or can be vulnerable to attacks of hackers. And against this type of threats, we've developed a technology called secure encrypted virtualization. So these, there is sometimes, there is almost like a mental shortcut thinking, well, we can secure just with software everything. But it's not really the case. I think that you need to have some hardware implementation as well. And the way that we do it, every single processor that we've got, there is a coprocessor, security coprocessor integrated in there. And this secure coprocessor actually performs 3 major functions. Number 1 is executes the secure boot. So at the time, within even this secure coprocessor, there is a small microcontroller, which is the first IP that is being initiated after the reset. And this microcontroller reads from the small area of non-volatile memory that we have integrated in the chip, reads the signature, and this signature and then authenticates the booting device, the flash device, and looks at exactly, is this signature matching or not? If it's not booting. If it's matching, it's going to the next stage. And the secure boot that we've implemented is much more comprehensive, going through authentication of BIOS, going through authentication of hypervisor operating system, and only at that time is initializing the entire system. So this first function of this coprocessor. The second function performed by the security coprocessor is generating and maintaining encryption keys that will be used with the system, in the system, for many different cases and uses. It will be used for instance, IPsec, but it will be used also by the next block that I'm going to describe in a second as well. And the third function of this coprocessor is to accelerate cipher processing. So SHA, DES, triple DES, AES, all of these ciphers can be accelerated, are being accelerated by this coprocessor in our system. So looking at, first of all, how do we do that? How do we protect against these threats that I've mentioned earlier, and how do we secure the memory? So this is the second part of the hardware that we've implemented. So in every single DDR controller, there is an AES-128 engine integrated. And this block actually on a fly encrypts and decrypts the writes to the memory and reads from the memory. Again, the keys are being generated by the security coprocessor. What it does is protects against, there is one key that actually secures the entire system. So this key is being used by operating system, by the hypervisor, and all of the users. All of the VMs will be using exactly the same encryption key. And again, so in this case, you can encrypt the whole and protect entire memory, or you can actually be very selective, because this encryption engine will be able to do it on a page basis. So you've got a granularity of 8K bytes. So you can decide that certain portions of memory, of your system memory, are not as important, or they are not as vulnerable than others, for instance. What it does in this case, so it protects against any physical attacks. One beauty of this technology is that you, as a user, you don't have to change any of your code. All of the data, or all of the modifications, are being done on the level of BIOS, operating system, and hypervisor. So all of that is being done by our partners, and they work on implementing and enabling this technology. I know what you're thinking. Okay, this is a great storage, but it will cost me. It will cost me performance. It will cost me, my cycles. So the good news is actually we've done quite a bit of benchmarking. In this case, what you see is a spec-int and different subsets of the spec-int benchmark suite. And we concluded that actually the impact is less than 2%. It's 1.4% on geomean. Okay, and worst case there's MCF, and this is less than 4%. So what it means is, this is almost negligible, to looking at the benefits that you will get from protecting the memory and protecting your system with the impact of 2%. So think it this way: if your DDR speed is 26667, megatransactions per second, then you will be at 2615. Okay, so this is really negligible number in here. We've got another technology that we've developed and which protects you even further. So here's a scenario, okay? You've got an entire system encrypted with the same one key, okay? You are not protected against a leaky hypervisor, or you are not, for instance, protected against a VM or user that escapes the sandbox, for instance, and does the modification or leaks the data. There is a solution that we've developed that for every single user, for every single VM, or a container, because this technology applies to containers as well, we generate a separate key. So every single user has the key that encrypts its own memory. Hypervisor doesn't know this key at all. So again, if there is any leakage of this hypervisor, you're good. You're protected because your data is protected with your own key. There is also a protection against the different VMs. And there is a use case. One of the universities in US got very, very excited about this technology because their use case is, like any university, they've run several of virtual machines for students' data, but they also have a medical school with a lot of patient data. And in their own words, thinking that one day there might be a bug and might be the patient data may leak to the student's domain is a nightmare. This technology protects that, because even if this leakage takes place, okay, the data is completely protected and completely encrypted. There is another use case that is very interesting as well. And this use case allows you, for instance, if you've got a system with your own VNFs, okay, and you are going to implement a third-party VNF that, you are not completely 100% sure. It's not your technology. You don't control everything. You can cryptographically isolate it with this technology. So you are restricting the risk or limiting the risk that you're going to have in there. Like with the previous technology, you don't have to modify any of your code. Everything is going to be taken care of by operating system and hypervisor vendors. And again, the impact of this technology is only about, in terms of the latency, is about 6%. So again, this is a very, very low number in terms of performance. We've done also a different benchmarking, and we've done the streaming, looking at copy, scale, add, and triad. And again, what you will see in here is that this data, the impact is maximum 2%. This is the biggest impact that you will have. So again, you will be able to get a really high level of protection of your system, not only end-to-end, but also in your own site by implementing this technology with a really low impact on your latency and on your performance. Here is one extra step that we've taken, okay? We tend to think about hypervisor, and giving hypervisor access to the data and handling our data for us. But there are two perspectives into that. Obviously, as a user, as a guest, you are acutely aware that you don't control the hypervisor. You don't even know when there is any being intrusion or hypervisor is being compromised. Yet you entrust all of your critical data, whether it's financial data, design details of your new product, or for instance, customer data, and you host this data there. So there is this worry about, yes, we allow that and we hope for the best. Now, hypervisor actually looks into that and says, well, hypervisor vendors, and we speak to them, and they say, well, we want to be out of the trust chain because you're entrusting us with data, and we will be liable if something goes wrong. If someone perpetrates our technology, if someone just does a hacking of our system, we want our customers to feel safe with that. We don't want to handle your data. We don't want to see your data. So actually, both of these perspectives are overlapping, and they're saying, okay, hypervisors should have as restricted visibility of your data as possible. So we've taken this technology even further. So I've mentioned about the fact that hypervisor has a different key, and virtual machines that you've got can be protected with a separate key. But there is one area that it's still hypervisor can see it, and this is the loophole that we are closing with this technology, which is called encrypted registers. Okay, so what is happening at the time that a virtual machine runs? The registers, the register numbers are, unencrypted and are in a system. However, at the time that there is either an interrupt and your virtual machine is stopping, hypervisor takes over, and at that time reads all of the registers and puts in its own memory space. And what it means is there is a lot of, at that time, again, the hypervisor becomes the area that is a weak link because it could be hacked, for instance. So we are removing this loophole as well by encrypting actually the register set. Why is this important? If someone knows what they're looking for at this time that there is an interrupt, okay, they can read the value of the registers. And for instance, if you get XMM register, typically this is the area where your AES encryption key is stored. Okay, so you can get actually all of the encryption data keys details very easily read. Okay, if someone modifies certain registers, for instance, your instruction counter, then they can increase this and bypass certain critical security checks, for instance. Okay, so this is a critically important. So what we are doing with this technology is we are giving the user, the guest, actually the complete ownership of that and driving the process. We are taking from the current situation when hypervisor is in complete control to the user, giving initiative to the user, and user decides which registers can be viewed and read by the hypervisor, which are not. In addition, also the user encrypts all of the registered data with their own key. So again, this data will be completely invisible, or it will be unusable by the hypervisor and by the hackers who managed to hack the hypervisor, actually, in this case. So in summary, what you can see is that we are tightening, we are reducing actually the surface of attack by really securing the systems even further, going from a completely unencrypted memory to memory that is encrypted with one key and shared by all of the VMs, up to the situation that you've got VMs and guests with their own encryption keys. And even closing the loophole of the fact that hypervisor at a stop and resume handles registers. And we are closing actually this loop as well, just to make these systems much more secured. And with that, thank you very much for your attention.